Hi, welcome to our fifth video, which is the second video about polynomials, thus the name Polynomials Part 2. And this time I'm actually giving a little mini agenda for this video so you can tell how it's going to be different from the last one. We're going to be talking about completing the square. We're going to start talking about polynomials that have degree bigger than 2, ones where we can't use things like factoring in the quadratic formula so easily. And then we're going to talk about both polynomial long division and synthetic division. Okay, so just to kind of finish off the topic of quadratics, we're going to talk about completing the square, which is the third method of solving quadratics after factoring and the quadratic formula. Now, the reason you might want to use completing the square over those other methods is that in the middle of it, it actually gets you into something called vertex form, which I'm going to be talking about as I talk about this problem. The best way to explain completing the square is to do an example. So I have an example here. I want to solve 2x squared minus 8x plus 3 equals 0. Okay, so here's what I'm going to do first. I'm going to walk us through this calculation I did earlier. So first, because I have a 2 out front, I want to factor that out, but only from the first two terms, so not from the 3. And if I do that, I get 2 times x squared minus 4x. Okay, so if there's no 2 out front, if the number is just 1, this step you can skip. Now, this number here, which you can think of as your b, is the number that we're going to do a quick mini calculation. Sometimes I do this calculation in my head, but I'm going to write it out for you guys. So this minus 4, the calculation is always divide it by 2 and then square that number. So if I divide minus 4 by 2, I get minus 2. And then if I square minus 2, I get 4. And that number, positive 4, is what I'm going to both add and subtract inside this parentheses. Okay, now the reason I'm adding and subtracting it is so that I'm not actually changing anything, because when I add and subtract the same number, nothing has actually changed. All right, next I need to get this minus 4 out of the parentheses, and I can't just move it out of the parentheses because I've got this 2 out front. So I have to move it out. To move it out, I need to multiply it by 2, and that's how I end up with minus 8 plus 3. Okay, now the important thing is what's inside the parentheses is a square. That's why we call this completing the square. What's it the square of? Well, it's the square of x minus 2. And I know that, well, one, because I can check, but I also know that because this minus 2 is the middle number in this calculation when I first divided by 2, but before I squared. So it's x minus 2 squared. And now here's, before I keep going in the calculation, what I've done is I've just rewritten this polynomial in something called vertex form, which looks like this. And the reason it's called vertex form will become clear a little bit later. All right, so I'm going to scroll down. I'm going to now ready to set this equal to 0 and solve over here on the left. And to do that, well, I think it's pretty straightforward, the algebra. First, I'm going to move over the minus 5. Then I'll divide by 2. Now I have a square here, so when I square root, I have to remember that there's both a plus and a minus square root to any positive number, so I need both of those because I'm looking for all solutions. And now I just move the minus 2 to the other side. So I end up with x equals 2 plus or minus the square root of 5 over 2. So just be careful here with your square roots. I might be able to simplify that a little bit, but honestly, I think this is a fine way to give the solution. And it is exactly what you'd get from the quadratic formula. In fact, completing the square is one way that you can prove the quadratic formula. So they are going to be saying the same thing. Now I'm going to come back to this vertex form for a second, because I claim that this actually gives you a nice way of graphing this quadratic if you had to graph it without a calculator or Desmos. And that's because it reveals that this quadratic is just a series of graph transformations being done to x squared. So let's think about our graph transformations for a second. What have I done to x squared? Well, first I've moved it to the right 2 units. Then the multiplying by 2 is going to be a vertical stretch. And then I've taken the whole thing and I've moved it down 5 units. So there's 3 graph transformations that have been done to this thing. So if I wanted to give a rough sketch of this, I could draw the normal x squared graph, but moved 2 units over, 5 units down, and then kind of stretched so that it's a little bit skinnier than it would be otherwise. And that's kind of as good as I can do. I mean, I should know that these x-intercepts should match up with these numbers, but given that I don't know square root of 5 over 2 over the top of my head, I can't do too much without a calculator. Okay, so let's talk about higher degree polynomials, polynomials with degree bigger than 2. So how can we think about them? Well, here's an analogy that I like to use with polynomials. It's actually a very powerful analogy. So if you think back to middle or elementary school, whenever you learned about this, any whole number can be written as a product of prime numbers. That's a very useful idea. Well, similarly, any polynomial can be written as a product of prime or irreducible polynomials. So polynomials that just can't be factored anymore. I'm going to be using the word irreducible in class, but I know the book likes to use the word prime, so I thought I would throw in both of these. Okay, so when you're looking for roots of a polynomial or solutions to setting the polynomial equal to 0, well, you're really looking for the factorization, and in particular, the linear factors in that factorization, because those are what correspond to the roots. Just think to factoring a quadratic. It's the same idea. So I'm going to give some examples of how this factorization might look. So here's one, just a normal quadratic. If we factor it like we did in the last video, we would get x minus 2 times x minus 5. So the roots are 2 and 5, because that's what I get for x if I set this equal to 0. On the other hand, the quadratic x squared plus 4 doesn't factor. You can use the quadratic formula to check that if you like. So we say that it's irreducible. That's why this polynomial doesn't have any roots, because it doesn't have any factors of degree 1. Right, now let's move on to higher degree things like this cubic. Now, I claim that this cubic factors as such. And even though maybe you don't know how I found that factorization, you can at least check it if you had to by foiling this all out. But if you believe me, then what this says is that this cubic has one root, x equals minus 1, and that's because it has this one linear factor. And if I set this equal to 0, the only solution would be x equals minus 1. All right, and lastly, I'll show you this big one that I just made up. This is a degree 5 polynomial, and I claim that this is the final factorization, and that it doesn't factor any more than this because this quadratic is irreducible. So if that's true, then what this means is that this polynomial has 2 roots, x equals 3 and x equals minus 1. This root over here, notice that it's to the square, and when that happens, we say that this root minus 1 is repeated, right? That's the definition of a repeated root. And another thing we can say is that because this is a square, we say that this root has multiplicity 2. So what it's kind of like is it's saying that we would sort of expect this to have 3 roots because there are 3 linear factors, but because 2 of those linear factors are the same, we say that there's 2 roots and that one of them has multiplicity 2. Okay, so what I'm going to talk about next is long division, which is one of the ways we have of dealing with polynomials of degree higher than 2. And what you're going to see is you're going to see me actually working this problem out on the board. Hi. Okay, so suppose that we have this cubic here, x cubed minus x squared minus 14x plus 24, and I can't use the quadratic formula or factor that very easily because it's a cubic. But suppose I do know that x equals 2 is a root. Then I can use a method called long division to find out what the other roots are, if there are any other roots. And the important thing to know about long division is it's actually exactly the same process as long division for numbers when you get down to it. It's just going to look a little bit more complicated. So I'm going to walk us through now. If you're feeling comfortable with this, you can actually skip to the end when I have the entire computation worked out and just check it that way to save a little bit of time. Okay, here I go. So I'm going to start out by writing the polynomial again. Okay, and beside it, I'm going to write the factor that I know about coming from x equals 2. So I know that x minus 2 is a factor, and I want to find out what the big polynomial divided by the factor is. So the important thing to remember about long division is that you only have to pay attention to what the leading term is when you're actually dividing it. In some ways, that actually makes it easier than regular long division because you actually don't have to do much division, strange as it sounds. Okay, oops. So what I'm going to do is I'm going to write x squared, because how many times does x go into x cubed? X squared times. Then I'm going to multiply x squared by the entire x minus 2. I get x cubed minus 2x squared. Then just like regular long division, I'm going to divide. This x cubed goes away, but minus x squared minus 2x squared. Well, the minus becomes a plus. So I get minus 1 plus 2, which ends up being 1. So this is x squared. Now, how many times does x go into x squared? X times. X times x minus 2 is x squared minus 2x. I carry down the minus 14x. Subtract again. Again, the x squareds go away, they should. And minus 14 minus 2 is minus 12. Okay, how many times does x go into minus 12x? Again, just looking at leading terms. It goes in minus 12 times. Minus 12 times x minus 2 is minus 12x minus 12. Or sorry, minus 12 times 2, which is plus 24. And I subtract again, and this time everything goes away, and I get a 0, which is good. That tells me that the remainder is 0, and since I know that x minus 2 goes evenly into this, because 2 is a root, I know that that remainder has to be 0. If that remainder was not 0, I know I would have done something wrong. Okay, so I finished up the division, and what I've concluded is that, I'm going to write the polynomial again, so it's a little overkill. This polynomial is equal to x minus 2 times x squared plus x minus 12. That's what the calculation gave me. And now what's left here is quadratic. So I can use factoring or the quadratic formula to take care of that last part. And it factors, in this case, it factors pretty easily into x minus 4 times x plus 3. Okay, so I finally found a full factorization for this cubic that I started out with. And I even know what the roots are. I know that the roots are x equals 2, 4, and minus 3. Not in order, but who cares? Okay, now we're going to solve the same problem, but with another method called synthetic division. Now, synthetic division has two obvious advantages over long division. One is that it's a lot faster. Two is that because it's cleaner, you're actually less likely to make mistakes. There is one significant downside, though, which is that you just have to memorize how it works. I personally, because I learned this as an adult, have never really memorized this, and every single time I teach it, I have to relearn it myself. So that tells you a little bit, but I know plenty of people who swear by synthetic division, and honestly, it's one of those things that I kind of wish I just memorized and don't have to relearn every single time. Anyways, here's how it works. Okay, so suppose, again, I have the same cubic I had before, and again, I have to start with knowing what a root is. All right, so to start this, I first write out not the polynomial, but the coefficients from the polynomial. So I'm going to write out 1 because that's the leading coefficient, minus 1 is in front of the x squared, minus 14 is in front of x, and 24 is the constant term, and I have to bring those minuses. Okay, so now I'm going to drop a line like so, and the root I'm just going to put right here. Keeping in mind that that's the root itself. Even though the factor is x minus 2, I actually want to put the root 2 here. Okay, so the first step of synthetic division is easy. I just take the leading coefficient and I drop it down here. Okay, so next I want to take 2 times this 2 times 1 equals 2. Minus 1 plus 2 is 1. 2 times 1 is 2. Minus 14 plus 2 is minus 12. 2 times minus 12 is minus 24. 24 plus minus 24 is 0. And I'm done. So what has this taught me? Well, these numbers down here are the coefficients of that division that I was looking for. That's actually the same result as the long division if you go back and look at the long division. This 0 here is actually the remainder. And again, it's good that that remainder is 0 because I know that 2 is a root. So if I didn't get 0, I would go back and start again. Okay, so I'm just going to write again, what has this taught me? This has taught me that my starting polynomial, minus 14x plus 24 equals x minus 2, and here's where I read off these numbers, times 1 times x squared plus 1 times x minus 12. And once again, I can factor this quadratic part to give me x plus 4 times x minus 3. So once I find these numbers, I do exactly what I did before. There's no trick to that. And I'm left with that full factorization at the end.